Mark, go ahead.
Okay, well, welcome to our revamped OTTER chat for 2023. So we have John McCarthy from WashU. He'll be talking about, I guess, two open problems or two problems he's been thinking about recently. So, and I assume he's going to explain the title for us. So take it away, John.
Well, thank you, Merrick, for the invitation to talk, and thank you all of you for showing up. My aunt married a man called Malcolm Otter, so her last name became Otter, and they lived in Nottingham. And as you may know, it's common in England for people to have names, not just numbers on their houses. So they always named their house the Holt, which is the a naturalist name for an otter's den. So hence the title. Okay, so Merrick asked me if I would talk about some open problems in operator theory. And often when people talk about open problems, they come up with things that are very hard, they're totally stuck on, which is occasionally useful, but normally it's hard to see how one would get started on them. So I decided instead I would take a couple of problems that I've actually been thinking about and see a way into, but I recently got distracted. I'm spending the semester in Berkeley, and I suddenly got distracted by a different problem. So these have been temporarily shoved aside, but I think they're tractable, which is why I thought they might be more appealing to this audience. So let me start with the first one. And I may not get to the second one, depending on how much time I spend telling you about the first one. So we start with the Muntz-Zatz theorem. So let me remind you what the Muntz-Zatz theorem says. Muntz-Zatz. And I think the accent goes that way on Zatz. The question they asked, and actually Bernstein asked, the question they answered is, suppose I take some set of natural numbers, and the natural numbers do include 0. And then I ask, if I look at the closed linear span of the powers of x inside L2 of 0, 1, well, if I take every power of x, this will give me every polynomial. So by Weierstrass's theorem, I will get all the continuous functions and hence all the L2 functions. So they asked, when do I get all of L2? What's the condition on the sequence nj that says it's dense enough for this to happen? And the answer is if and only if the sum of 1 over nj is infinite. And let me give you one proof of this. That this was proved in, I think, 1916, and there's various proofs, all of which rely sooner or later on complex analysis, even though I want to emphasize it's a real analysis question. It's all about L2, but every proof I've ever seen relies on you build some analytic function, and you know something about its zeros, and then it boils down, and something about the class that this function lives in, and it boils down to a question of, can you have a non-zero function in this class of analytic functions that vanishes on this set? So there's various ways of doing that, but that's the basic idea behind every proof I've seen of this. Oh, except one, except Zatz's original proof, which I'll also talk about later. Okay, so here's one proof. Suppose I calculate the inner product of x to the m with x to the n in L2. Well, that's not very hard. This is just the integral of x to the m plus n, and we can all do that. Now, suppose I temporarily move from L2 of 0, 1 to the Hardy space H2. So please feel free to stop me at any time to ask questions. One of the difficulties of giving a Zoom talk, especially since I'm using an iPad and a phone, so even if you've left your camera on, I can't see your faces. is I can't tell who's nodding, who's frowning, and who's reading the newspaper online. So please, if you have any questions, or if you think anybody else has a question, feel free to ask it on their behalf. So H2, this is the Hardy space. It's the set of holomorphic functions on the unit disk, such that they're Taylor series or square summable. And inside H2, you have the Sega kernel, which is the reproducing kernel. This has the property that if I take any function in H2 and take its inner product with KW, it just shoots out the value of KW. So now, inside H2, let's do the following calculation. Let's take the inner product of 1 over m plus 1 times the Sega kernel at the point m over m plus 1. And we'll take the inner product of that with the same thing with the m's replaced by n's. Calculate this inner product in H2. And what do we get? Well, the constants come out. So I get 1 over n plus 1 times 1 over n plus 1. And then I'm taking a, let's see if I can do this. I'm taking a kernel here, inner product, a kernel there. So I just evaluate this kernel at the point n over n plus 1. So this will give me 1 over 1 minus m over m plus 1 times n over n plus 1 from this. And I do a little algebra here. I multiply through by n plus 1, n plus 1. This gives me 1 over m plus 1 times n plus 1 minus mn. And that is the same as 1 over m plus n plus 1. Notice that these two numbers, or these two expressions, are identical. So that tells us that the inner product of x to the m with x to the n in L2 is the same as the inner product of, associated with m, I have this vector here in H2, and associated with n, I have this vector here in H2. So that says that if I define a map U that sends some, say, finite sum, Cmx to the m, and it maps it to Cm times, I replace x to the m by 1 over m plus 1 times the Sega kernel at m over m plus 1. Our calculation has said that U is an isometry from, so this maps L2 to H2. And our calculation here says that if I take the inner product of two such expressions before and after I apply U, I get exactly the same thing. So we're going to call U the Saracen transform, because Saracen did a slightly different thing, but basically the same idea in a paper of his from the early 60s. And the Saracen transform is a unitary. It's fairly easy to check that it's not just an isometry, but it's a unitary from L2 to H2. Well, so now the Muntz-Zapt question, we want to know when the span of x to the m is dense in L2. This is a span, not a U. That's exactly the same as when the span of the kernel functions at m over n plus 1, because the constant before it isn't going to affect what the linear span. When this is dense in the Hardy space. And that's now a straightforward question to answer. The Hardy space is a Hilbert space. So to know if something is dense, the question is, can I find a non-zero function that's orthogonal to every element in this set? Well, so if I take the inner product of f with k m over m plus 1, that's just, since it's the reproducing kernel, I just evaluate f at that point. And so now the question is, does there exist some non-zero function in, oh, sorry, these were not all. This is some subset of the natural numbers, f, m, j plus 1. So the question now becomes, is there a non-zero function in H2 that vanishes at mj over mj plus 1 for every mj in your set? Well, zero sets in H2, the subsets of the unit disk on which you can have a non-zero H2 function vanish, are exactly characterized by the Blaschke condition. So there exists a non-zero f such that f vanishes on some sequence zj if and only if the sum of the distance from zj to the boundary is finite. So in our case, this will become the sum of 1 minus mj over mj plus 1, which is the sum of 1 over mj plus 1, is finite. So this is the contrapositive, that the set of functions is not dense if this sum of the reciprocals is finite. So that's the same as the way I stated earlier, the set is dense if this sum is infinite. Okay, so that's a proof of the Mundt-Zatz theorem. Now, let's modify the question a little bit. You can think of the Mundt-Zatz theorem as asking, suppose I take an increasing, so suppose I take some set S, Sk, say. So this would be the first X, what was I calling? Xn, Xm1. I can look at the linear span of, the first k elements in the set. And then as k increases, these spaces Sk get larger and larger. And I can ask, as k goes to infinity, what do I get? Do I get all of L2 or do I get something smaller? So let's modify that now, but instead of strictly increasing sets, we'll have sets that change. So let's consider m sub n to be the linear span of the powers of x going from n plus 1 to 2n. I'm only choosing 2 for convenience of when we're speaking. In general, you can replace this 2 by any real number larger than 1, and you take the largest integer less than or equal to it if it's not an integer. So then I can ask, so given mn, what is the limit of these subspaces? And by the limit of the subspaces, I mean the set of f such that there exists a gn in mn such that the norm of f minus gn tends to 0 as n goes to infinity. Well, let me make a couple of remarks about, so let's call this space, you give it a name, we'll call it, we'll call it M. Can we describe the space N, the limit of these subspaces M sub N? So I claim we can. So we observe the following. M has the property that it's invariant under multiplication by x. Why? Because if I take m sub n and I multiply it by x, I live inside m sub n plus 1. So m sub x of mn is contained in mn plus 1. And so the limit of these spaces will contain the limit of multiplication by x applied to mn. Well, that's a pretty powerful statement right there. If I look at subspaces, it's also obvious that M is a linear subspace. So, and by definition, it's closed. So we have a closed linear subspace of L2, 0, 1 that's invariant under multiplication by x. So those are fairly easy to describe. They are precisely, that says that M has to be L2 of E, where E is some measurable subset of 0, 1. So it consists of all functions in 0, 1 that are 0 almost everywhere outside of E. You can prove that using the spectral theorem, or you can prove it directly using just the density of the polynomials in the continuous functions. But I claim E can't be any old interval because there's another observation. There's an operator called the Volterra operator, which is just integration. Vf at x is the integral from 0 to x of f of t dt. And notice what v does to monomials. V of x to the m is 1 over m plus 1, x to the m plus 1. So by exactly the same argument as in part 1, so what we're really using here is that multiplication by x sends x to the m to x to the m plus 1. The Volterra operator does roughly the same thing, except I have some constant behind it. So by exactly the same argument, v leaves m invariant. Well, if I ask what sets of the form L2E are left invariant, notice that if I take the characteristic function of E and I integrate it, so if suppose E looked kind of like this set here. So if I take the characteristic function of E and I integrated it, I'd get something that, and I do this in a different color, not blue, let's do it in pink. It would be 0 to start with, then it would increase a bit, then it would stay constant, then it would increase a bit, then it would stay constant, then it would increase a bit. So I get a function like that. In particular, if once E starts, there was ever a gap in it, here, V would not leave invariant a function that is 0 off E, because here it's non-zero. So you can make this into a rigorous argument and say that if L2 of E is invariant under the Volterra operator, E has to be an interval that of the form R1. So M has to be of this form for some R between 0 and 1. Just using these two properties, that is invariant under multiplication by x and is invariant under the Volterra. This is actually a harder theorem due to Donahue and two people proved it simultaneously. Brodsky, Donahue and Brodsky in the 60s proved that the invariant subspace lattice of the Volterra operator is exactly spaces of the form L2R1. It's harder to prove if you don't know in advance it's also invariant on multiplication by x. If you know it's invariant on multiplication by x, it becomes much easier. Okay, so using these two observations, let's go back to our question. Here's Mn. We ask what the limit of these spaces is, and I've told you whatever the limit of the spaces is has to be of the form L2R1 for some R. So we've just shown that this has to be L2R1. So the only thing that remains to determine is what is R. Here we are. Let me rewrite that. The limit as n tends to infinity of the spaces Mn is L2R1. And the question is, what is R? Well, here's one way of there's two ways of one can find this. We can use the Saracen transform. U of Mn, well, this is inside H2. It's the span of the kernel functions at the points, n plus 1 over 2n plus 1, 2n plus n plus 1, 2n plus 2, n plus, hold on. For any point n, it goes to n over n plus 1. So if it's n plus 1, that'll be n plus 1 over n plus 2. Sorry, oops. Okay, n plus 1 over n plus 2, all the way up to 2n goes to 2n over 2n plus 1. Yeah. So this is a span of kernel functions. You can ask what the limit is, and you can, if you're good at calculations in the Hardy space, you can show that the limiting space M is of the form S H2 perp, where S is a singular inner function with a single atom at 1. And you work out exactly what W is. I think it's log of a half. And then you can work out, you can then invert that and find out what R is. That gives the solution R is a quarter. You can also, so I said at the beginning that all proofs of the Muntz-Zatz theorem rely on something in complex analysis. That's not true. And that was a stupid thing of me to say, because Zatz's original proof didn't. Zatz's original proof relied on a Hilbert space argument, which is this. Since I know that M is of the form L2R1, and I just need to determine what R is, suppose I calculate the norm of the projection onto M perp of the constant function 1. Well, that's pretty easy. This is just the integral from 0 to R of 1, which is R. On the other hand, if I calculate the distance from 1 to Mn squared, so I take the limit as n goes to infinity of that, this will be the distance from 1 to m squared. So from what we just said, this is R, but this, it turns out, is straightforward to calculate. There's a general formula that if I want to calculate the distance of one vector in a Hilbert space from the linear span of some other vectors, I calculate it's a ratio of determinants. I take the determinant on top. I take the inner product of 1 with every vector in my space, x to the n plus 1. Sorry, 1 with one with x to the n plus 1, 1 with x to the 2n, and then I do the same thing here. I take the next vector in the space, which is x to the n plus 1. I take the inner product of that with 1, x to the n plus 1, x to the n plus 1, x to the n plus 1, x to the 2n. So on top, I'm taking from the set 1, x to the n plus 1, x to the 2n. I'm taking the gram matrix of every pair inner product with the taking their inner product. Now on the bottom, I do the same thing, except instead of an n plus 1 by n plus 1 space, I take everything excluding the function 1. So here I take the n by n gram matrix. And so this is just a particular case of the general formula if I want to calculate the distance between any vector in a Hilbert space and any a space spanned by any other set of vectors. I just take the ratio of these determinants, and I guess I need an absolute value in to make sure I get something positive. And that'll give me the square of the distance. Now, at first sight, this looks a little daunting, but fortunately, there's a theorem of Cauchy from something like 1826, in which he very kindly worked out exactly if I take so each of these inner products it is of the form 1 over m plus n plus 1. And Cauchy worked out a formula for the determinant of these things, and it's a massive product. Each determinant is a product, which, fortunately for us, since I have very similar factors in the numerator and the denominator, there's massive cancellation, and the quotient, you just use Cauchy's formula, calculate the quotient, and your quotient is something like n plus 1 over 2n plus 1 squared. That may be exactly right, but it's something like that. And as n goes to infinity, this clearly tends to a quarter. Okay. That's all the background. Now I get to the problems. Everything I told you was done in L2. But I would very much like to know what happens if we replace L2 by LP for some P, say, finite. For P not equal to 2. And let's take P finite for simplicity. I think if P is infinite, all the questions are going to make sense, but you'll need a weak star closure instead of a norm closure. So I'm going to ask several questions here, all of which are open and in increasing order of difficulty. So question 1. So we're now going to fix P. Fix P not equal to 2. What is the limit, as n goes to infinity, of the span of x to the n plus 1 through x to the 2n? Now, just as before, let's call this m again. So as before, I still have that m is invariant under multiplication by x, and it's also invariant under the Volterra operator, just integrating. And so now you can't use the spectral theorem, but you can use a more direct polynomial approximation argument to, again, I can use this first fact here to show that M has to be of the form LP of E, all the functions that vanish off the set E almost everywhere. And I can use the second thing to show that E then has to be an interval. So we get M is LP of R1. So R depends on P. So R is some function of P. And I want to know what is it. So the obvious things we know R of 2 is 1/4. Let's see. As P increases, the LP spaces on 0, 1 decrease. So I think we get that R of P is a non-increasing, so decreasing but not strictly necessarily, is a non-increasing function of P. And C, you can show that R of P is always at least a half. I'm not going to prove this now, but if you're interested, if you look on my homepage, there's a recent paper with a title, something about Hardy's inequality, that'll give an argument for C, and also repeat all the arguments. So Hardy's inequality revisited, I think it's called, a paper with Jim Agler on my homepage or on the archive. We'll repeat the previous arguments, put them in context, and give a proof of C here. So I can come up with various guesses as to what this function will be. I suspect there's going to be a formula for it, which may be different if P is bigger than 2 and less than 2. I'm not sure. Well, I don't know what happens in any P not equal to 2, but I think this is an interesting problem for reasons I'm going to get into. And I think it's tractable, and I hope somebody in the audience will solve it. And if nobody does, if you do, please tell me. And if you don't, I intend to get back to it and think about it more in a while. But I think this is a solvable, interesting problem.
John, are you offering a prize for this problem?
Yes, I will send you a thank you by email.
So not worth a bottle of champagne.
No, it's not worth a bottle of champagne.
The prize is that the person who proves it gets the royalties on the video.
Oh, that's a gem. I was planning on retiring on those royalties. I'll have to think if I'm willing to make such a generous offer. Maybe a fraction to be determined based on the ingenuity of the proof.
Fair.
Okay, so why is this an interesting problem? Okay, so here's the background. We have the Volterra operator. F goes to the integral of F. There's a related operator called the Hardy operator, where it's similar, except I divide by X. And it's called the Hardy operator because Hardy showed it's not obvious when you divide by X that things stay bounded, but Hardy showed that H is a bounded operator from LP to LP for all P strictly bigger than 1. And notice H sends X to the N to 1 over N plus 1 X to the N. Now, we can apply the Saracen transform to H, and we get an operator on the Hardy space. It's actually a well-known operator. It's 1 minus the backward shift. This was proved or observed by Brown, Halmos, and Piercy sometime in the 50s. So the Hardy operator on L2 is up to this relatively simple change of variables. I guess 1 minus the adjoint of the Hardy operator is unitarily equivalent to the shift. And so its invariant subspace lattice, so the invariant subspace lattice of the Hardy operator is going to be this, after you apply the Saracen transform, the same as the invariant subspaces of the backward shift. The invariant subspaces of the backward shift have been studied very intensely ever since they were first described by Berling. So Berling's theorem tells you the invariant subspaces of the forward shift are just things of the form. So if S n is contained in n, sorry, S here is the, I should have said, multiplication by Z on the Hardy space. So Berling's theorem says that all invariant subspaces are of the form U times H2, where U is inner, and therefore all invariant subspaces of the backward shift, let's call this M, implies M is of the form U H2 perp. This is called a model space. So these have been studied extensively using complex analysis on the Hardy space. But you can think of them, everything you can say about them, you can translate and say about invariant subspaces of the Hardy operator on L2 of 0, 1. So you can now use this as a way of studying L2. So L2 of 0, 1 is perhaps the most fundamental Hilbert space, one of the building blocks of analysis. And understanding this is the basis of a huge part of mathematics. And normally you study L2 using exponential functions, which have lots of virtues. I'm not dissing exponential functions. But this is a way of thinking about, let's study L2 instead of exponentials, let's use monomials. And this will shed a different light, which may tell us something else. In particular, the Saracen transform is great if you care about L2. But if P is not equal to 2, as long as it's bigger than 1, I still have the Hardy operator maps LP to LP. And I can ask, what are its invariant subspaces? This is a big question. So this one I will give a prize for. So I will give a bottle for this prize. To the astute, this is supposed to be a Bordeaux bottle, not a Burgundy bottle. But I guess I've kind of messed up the sides. Now, so this I think is a very hard problem, which I would love to know the answer to. But there's the way one approaches very hard problems is you break it up into more reasonable steps. So the first question, or not the first question, but a sub-question is every subspace a monomial space, every invariant subspace what's a monomial space? Well, so suppose I take a span of monomial functions where the powers lie in some finite set. So Fn is a finite set. And the SJs, well, I want these all to lie in LP. So I just want the condition x to the SJ is in LP. And if you work that out, that's the same as saying the real part of SJ is larger than -1 over P. So SJ no longer has to be a natural number. I claim that any space like this, so if we were in L2 and we did the Saracen transform, this would give us a span of kernel functions. Kernel functions are eigenvectors for the backward shift, so it would clearly be invariant. But since the Hardy operator leaves monomials, it goes to 1 over Sj plus 1 times x to the Sj. Monomials are eigenfunctions for the Hardy operator, so the Hardy operator is going to leave any space like Mn invariant. And so we'll say a monomial space is anything that's a limit of, so we'll call this a finite monomial space when Fn is a finite set. A monomial space is by definition a limit of finite monomial sets, finite monomial spaces. So this is a finite monomial space. So in the case of P equals 2, this would be the assertion that every backward shift invariant subspace can be approximated by finite dimensional spaces that are spanned by kernel functions. And this is true, and it's proved in Nikolsky's book in a short and elegant way. But in a long and non-elegant way, Jim and I have a proof of this. True. But the novel feature of our proof is we don't use any complex analysis. We do it, the proof just uses L2 theory. But it does, however, rely on the fact that L2 is a Hilbert space. So the big question that's worth a bottle of something nice is, what are the invariant subspaces of the Hardy operator on LP? The sub-question is, can you at least say that they're all limits of monomial spaces? And that'll be worth a beer. So is every invariant subspace. Oh, if you don't drink alcohol, you can have non-alcoholic presents substituted for them. Is every invariant subspace of the Hardy operator on LP a monomial space? And let's see, I clearly don't have time to go on to the question about composition operators, so I'll ask one more question related to this circle of ideas. I just thought of a question. Now I've forgotten it again. Yes. The Hardy operator has the property that it takes every monomial and it maps it to itself times some constant. So you could ask in general, suppose T maps LP to LP and has the property that x to any power maps to some multiple of x to that power. when is T bounded? So what things can I put in here? What C's can I put in that make this bounded? Again, when P equals 2, this is straightforward. You can use the Saracen transform idea. This would be asking Ks over S plus 1 is supposed to map to C of S, K of S over S plus 1. So you're asking for an operator that leaves all the kernel functions invariant. So that means it has to be a function of the backward shift. And so you need to know that C of S is of the form phi of S bar, where phi is in H infinity. That's a necessary and sufficient condition for this operator on L2 to be bounded. However, the Saracen transform idea breaks down completely once P is not 2. So you still have operators like this. Some are bounded, some aren't. Can you characterize them? And I think this might be a medium hard question. It's probably you can probably prove necessary conditions and you can prove sufficient conditions. And my guess is that it'll be very difficult to close the gap entirely, but you may be able to get close. Okay, so I will not say anything about composition operators. I will stop here, and if anybody has any questions, please feel free to jump in. Thank you.